Hi, I'm John Miller, and today I'm going to talk about accuracy on the line, on the strong correlation between out-of-distribution and in-distribution generalization. This is joint work with Rohan Tari, Aditi Raghunathan, Shuri Sagawa, Panwei Ko, Vaishal Shankar, Percy Liang, Yer Carmen, and Ludwig Schmidt. We often deploy machine learning models in environments different than those in which they were trained. For instance, we train self-driving cars in sunny California, but then we use them on wintry roads in Michigan. We train systems to identify tumors for pathology slides using data from one set of hospitals, but then deploy those systems in other hospitals, where differences in data collection or pre-processing can lead to slides which look very different. It's also common to train systems to analyze satellite data using images from the United States, where labels are plentiful, and then use those systems to analyze data from Africa to answer questions about poverty or development. Now, in each of these cases, if we want reliable models, we need to understand and reason about their out-of-distribution performance. And a basic question one can ask is, how does out-of-distribution performance relate to the in-distribution performance of these systems? Now, much of the previous understanding of this question comes from domain adaptation theory. To understand what this theory says, consider the following scatter plot. On the x-axis, we have in-distribution accuracy, the y-axis, out-of-distribution accuracy, and on the diagonal, the no-change y equals x line. In domain adaptation theory, the key quantity is a measure of discrepancy between the original and the new distribution, which gives rise to a confidence band around the y equals x line, where all the model evaluations have to fall. Now, importantly, in domain adaptation, the structure or relationship between these model evaluations can be essentially arbitrary, as long as they fall within the confidence band. However, recent work in dataset reproductions has revealed a much more precise phenomenon. In particular, Recht et al. In 2019 attempted to reconstruct the ImageNet test set, creating a dataset called ImageNet v2, albeit with small changes in the original creation process, which lead to distribution shift. If we construct the same type of scatter plot as I previously described, we get a much more precise phenomenon. In particular, all the models lie below the y equals x line, dropping around 11% on average. And more importantly, the relationship between the original ImageNet accuracy and the new out-of-distribution ImageNet v2 accuracy is linear under appropriate scaling. This is much more precise than would have been predicted by domain adaptation theory. However, domain adaptation theory is very broad and covers essentially arbitrary pairs of distributions in any model. In contrast, this precise relationship in dataset reproduction, while interesting, has so far in existing experiments was limited only to considering sort of high-performing neural models and only concerned itself with reproduction shifts. So given the preciseness of this relationship between in and out-of-distribution performance, the question that we consider in our work is, how broad is the linear trend phenomena that we observed in this dataset reproduction setting? Does it extend beyond high-performing CNN models, and does it extend beyond dataset reproductions? In our work, we show the answer is a resounding yes. We consider a huge collection of different distribution shifts, or we consider more than 60 in our paper, and across this wide variety of distribution shifts, including different image tasks, both image classification and also pose estimation, as well as different types of distribution shifts, dataset reproduction, as well as synthetic, or also realistic dataset shifts coming from the Stanford-WILDS benchmark, we see this very precise linear trend. And importantly, the trend holds both for deep and classical models. So not just high-performing CNNs, but also classical models like random forests, KNNs, SVM, random features, etc. We consider a wide variety of different types of distribution shifts. For instance, considering land use classification from satellite images, where you also see linear relationships, as well as different tasks, like considering a synthetic pose estimation task, where we consider renderings of objects both in and out of distribution under texture and lighting shifts. We also see strong linear relationships. Now, there's a lot more discussion about our experiments and the trends we observe in our paper. And in particular, we don't just discuss cases where the linear trend holds. We also discuss failure modes and examples where the linear trend fails to hold. In particular, the Chameleon-17-WILDS dataset, which is a tumor slide classification task. We don't see a clean linear trend. We discuss why we think this might occur. We also talk about whether or not pre-training or training on additional data changes the trends that we observe. And finally, in the paper, we can discuss a candidate theory for the linear trends that we observe that goes beyond some of the results in domain adaptation based on a Gaussian data model. and simulations under the model give us this very precise linear trend that we observed. So I'd encourage you to check out the paper to learn more. Thank you.